So I got the Little Prince. If you ever read, how many people have read the Petit Prince? In the original French? No? Okay, sorry. Touch a nerve. All right. So we got this little prince here. We'll just call them P for prince or P for person, whatever you like, if you're not into the monarchy. So I don't really know how he became prince because he lives on a planet where he's the only inhabitant, if you know anything about it. But that's the way monarchies work sometimes. So we have this character that's on a planet anyway, and we're going to pretend that this is Earth. So the radius of the Earth is 6.4. Let's just round it off to 2 sig fig. 6.4, I know it's 6.38, times 10 to the power of 6 meters. The mass of the Earth is 6.0 times 10 to the power of 24 kilograms. And the mass of this person, we'll make it a nice round regal value of 100 kilograms. Okay. And we're going to state a couple of assumptions. And it wouldn't be obvious from this diagram. One assumption is that the height of the person is negligible compared to a planet. Height of person is negligible. This is one of the reasons, one of the many reasons, why The Little Prince is not probably physics accurate. But to have a person who doesn't have a negligible mass or negligible height compared to the planet on which they stand would be very problematic, and you can imagine they would jump off of this little asteroid in no time, and then they would float into space and suffocate if the planet could even hold on to atmosphere, which it couldn't, and so they would have died before we even started the story, and that would make it not a very interesting French tale. Anyway, so let's just suspend our disbelief on that one, okay? But we're sitting on this planet, and we're we're not very tall. What is the person's weight? That's our first question. What is the person's weight? A follow-up question could be, what's the mutual force of attraction between the person and Earth? Between and the person and Earth. And to answer those questions, we might just want to recognize that it's the same question. F big G and force of 2 on 1 could both be considered to be a way of measuring the weight of this person on the surface. So we're assuming that they're at the surface, at the radius of the planet, because weight is a force of attraction due to gravity. And so G times mass of the Earth times the mass of the person divided by radius of the Earth squared. End up getting 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared, and yes, you need to show these units and know these units, although they're going to be on your equation sheet anyway, times 6.0 times 10 to the power of 24 kilograms times, we said this person was 100 kilograms, all divided by the radius of the Earth, 6.4 times 10 to the power of 6 meters squared. I look at this and I think, like, this is not a very problem-solving oriented kind of question. This is the kind of question where you just plug numbers in. But the reason that I want to do it is to make sure that everybody actually can plug their numbers in, because there seems to be a technical problem with data entry for things with lots of scientific notation, and people find this in chemistry class as well. Could you please take a minute? Like, I mean, whether you've dealt with Avogadro's number before or universal gravitational constant before, take a minute, make sure you can do the data entry. Let's see what we get. Who's the quickest draw with the calculator? You? Evie, you got it?
977.05
078. Oh man! And here I feel like I gotta go second guess myself, because didn't I say 9.79? I gotta go back and fix that. That should be a 7, shouldn't it? Now I've got to... Oh, because we rounded the values. You're right. This is unrounded. All right. I'll leave that 9 in there. All right, with our rounded values, you're right. We get 9.7 or 977. So I guess if we hadn't rounded these values, it would have been closer to 979. You're right. That's where my mistake is. All right, well, I'll let go of my insecurity for a second. And we got to round it off to 2 sig figs. And either way, we're going to get 980. 980, oh, units, newtons. 980 newtons. If you're really committed to the 2 sig figs, you could say 9.8 times 10 to the power of 2 newtons. Now the nice thing about this is that if we hadn't rounded to 2 sig figs, we would have gotten G is equal to 9.7, what is it, 9.799? If we hadn't rounded to 2 sig figs for these two values, we would have gotten 9.799. This time we get 9.77 because we did kind of overround. But we get newtons per kilogram for that average gravitational constant around the Earth. Average gravitational, not constant, field intensity. Field intensity around Earth. And remember, average gravitational acceleration would be 9.799 meters per second squared, where we recognize the difference in emphasis of concept between the two units, right? How much force per kilogram versus at what rate we fall. But it ends up being the same value. And then, one of the great love stories of our time. Anybody remember their names? Phineas, Isabella. Yeah, see, you identify with Isabella. I love that. You didn't say that? Oh, okay. All right. I thought everybody did. I'm just joking, Audrey. All right. So we're going to give Isabella a nice cartoonish mass of 40.0 kilograms. And Phineas looks shorter, so we'll give him a mass of 30.0 kilograms. But look at the size of that head. And they find themselves about to do something that they may or may not get busted for at a distance of 0.200 meters. If you haven't seen the cartoon, then that sounds stranger than... Anyway, never mind. Phineas gets up to no good. Well, not no good, but like in a friendly way, right? Wouldn't you describe it like as hijinks? Yeah. Not romantic, usually. Anyway, and Isabella is attracted to Phineas, but what he doesn't realize is that he's also attracted to her. And in, I think, the series finale, they do get together when they go off to college, if you've seen this. It's really worth following up on, because it makes it all just make sense, all right? Anyway, I don't know why they needed to do that, but they did. I assume that it was real and not fan fiction, because I'm expecting it to be an in-universe truth. Anyway, F big G is equal to 6.67 times 10 to the power of negative 11 Newton meters squared per kilogram squared. And if you haven't seen this TV series, none of this makes sense to you, but that's okay. 40 kilograms times 30 kilograms. The point is, these two young people, they're meant to be together. And she says, Phineas, did you know that I'm attracted to you? And he says, well, actually, Isabella, I'm also attracted to you. The exact same amount, scientifically speaking. Okay, so if you guys can do the calculation on this, how much are these two young people attracted to each other? quantitatively. Starts with a 2. If you've done it right, it starts with a 2. What's that? 2.001. Yeah. 2.0. It takes 2, baby. 2.001 times 10 to the power of -6 newtons. So is he attracted to her a lot or a little at this point in the story? 10 to the -6. That's a millionth of a newton. We got a ways to go before the end of the series, okay? But not a lot. Now, the nice thing about this is that you too can profess your love in a fairly risk-free way to somebody at a physics party. You could say to that special someone, "Hey, fella. Hey, gal. Hey, honey." Whatever the thing that is that the kids say today. Did you know that you're attracted to me? And depending on the reception you get with that, you can go in a physics direction or a non-physics direction. But the physics direction is very proof is in the math. Okay, you can pull out your calculator, and that'll be a great way to meet people at physics parties. Okay, so that's just so you know. All right, and I'm sure that some of you are going into engineering, and that'll be something that really works for you. Others not so much. All right, so the other creepy thing is you could just announce to the room, as I'm about to right now. Did you know that we're all attracted to each other? A lot or a little? A little, right? Like, think about it. None of us are 20 centimeters away from each other. Well, maybe a couple of us, but not many of us, right? Like, not very close. Now, the reason I bring up this creepy reality is that if you were in interstellar space and there were a bunch of chunks of rock, wouldn't they be mutually attracted to each other? You know, like, if there's two, like these two lovebirds, wouldn't they eventually get together? What if there was another one? Do you think that over time, because of this mutual attraction, and it would be a complicated free body diagram, but don't you imagine that over time they would coalesce into one big clump? And what if they weren't rocks? What if they were like specks of dust in there too? Can you imagine that this is actually what the beginning stages are for, I don't know, nebulae, stellar fusion reactions? And so this would be a great follow-up to that party conversation. Did you know that the same kind of force of attraction that we're experiencing right now is what causes stars to ignite? Wow. And like technically, and this is your chemistry coming out, we're all made of stars. Like, wow. Like, this is where it really gets deep, you know? Anyway, let's do something else. So we got this. Don't do that. Don't say any of those things ever, okay? Yeah. Okay. Don't even ask Miss Killens if I used any of those lines. I did not use any of those lines, okay? I had a different, more creative things to say. Anyway, more statistically focused than physics focused. I love statistics. Anyway, radius of orbit, that's an interesting thing to talk about. Let's change the topic. It turns out that if you're talking about the radius of orbit for a planet, you might want to think about the actual radius of the planet. So like from the center of the planet outward, we could talk about the radius of, radius of Earth. I didn't give myself enough whiteout space here. I'm going to do that again. From the center of the planet outward, we'd have the radius of Earth. Okay? And then we could also talk about from the surface of the Earth out to an orbiting satellite, we've got an altitude. I'm just going to call it alt. If you weren't able to white out things because you don't own a whiteout, you could just radius the Earth out like this, okay? Okay, so we've got the radius of the Earth, we've got an altitude of a satellite, and if I wanted to talk about the radius of orbit, I would talk about the radius of the Earth plus altitude. Right, so from the axis all the way out to the radius of orbit. Now, if I had a telecommunications satellite, again, we're just going to, Gonna make a nice round number. Satellite being 1,000 kilograms. The mass of the Earth. We'll keep it at 2 sig figs just to be consistent for the page. 6.0 times 10 to the power of 24 kilograms. The radius of the Earth is 6.4 times 10 to the power of 8 meters. And let's make up an altitude. I was told by a student once in the past that was really into satellites that a decent altitude for a satellite of this type would be 2.00 times 10 to the power of 7 meters. Okay, he was really into satellites. I don't know why. But everybody gets fascinated. You know, Cavendish got fascinated about stuff. You just get excited about things. So if we wanted to figure out what the force of attraction was for this satellite, G, mass of the Earth, mass of the satellite, divided by the radius of orbit squared. We could expand that out. We could say G, mass of the Earth, times the mass of the satellite, divided by, instead of orbit squared, we could talk about this binomial, radius of the Earth plus altitude squared. But then eventually we're going to have to sub in numbers. Oh my gosh. Don't forget that all these brackets though, they're your best friend when you have to actually do the data entry. And so I really want to make sure that people can type this into their calculator. See if you can do it. If you have to use all of these brackets just to make it so you don't make a mistake, totally do that. Okay, so I'm being really careful. I'm putting brackets around each individual scientific notation term here, because I found that a lot of students mess that up. Somehow they make it be to the power of 72 or something like that. Now I'm going to ask you guys, how many people get an answer that starts with a 5? I got it. One person, fastest draw.
57.4207.
57.4207.
Yes.
All right. Anybody else have a different number? I got my decimal one place over. 574. I got 574. That's why I'm testing the waters, because sometimes I make a mistake too, right? It's okay. Probably there was like scientific notation mistake somewhere in there. 574? All right. All right. So no judgment. I mean, this is why we're doing a trial run, right? Because it's easy to do a quick little data entry error. But we would turn that into, it looks like we had 2 significant figures way back when. So 5.7 times 10 to the power of 2 newtons of mutual attraction between that satellite and the Earth. Now the nice thing about this, and we're not going to quite go in that direction just this moment, but wouldn't that FG, F big G, be equal to the centripetal force for that orbiting planet or orbiting satellite? Can you imagine that we could then take that information and recognize that that F big G value is equal to mv squared over r? And we could calculate what the orbital speed is for that satellite? I'm not going in that direction right now. I just want to say that that's something that's on the table because we've talked about centripetal force as well. Yeah. Oh shoot, it was 1,000. I apologize to you. I wrote 100 because I was still stuck on the little prints at the top corner of the page.
That's what happened.
It's a 1,000. You're right. That's why it's 574.
Oh,
All right. Thanks for catching that.